Probability. Let us look into the concepts first. Probability means the chance of happening. If there is a chance, then only probability will exist. For certainty, we won't talk about the probability. Suppose if it is raining, what is the chance of raining? It's meaningless. A running race is conducted. Only one participant is there. Who is the winner? There is no possibility of chances. Certainly he is the winner. If there is certainty, then no need to talk about the probability, or else the probability of certainty is 1. Okay, for chances, if there exists a chance happening of one thing, if it varies in each and every experiment, then probability will arise. For example, explanation of concept, explanation, coins, dice, playing cards. Let us look into these things. First of all, we're taking coins. In this, coin will have two sides. One is a head, it is denoted by H, and the other side is we call it as a tail, denoted by T. Head and tail, just we represented with the H and T. If a coin is tossed, what are the chances of occurrence? If a coin is tossed, the chance of occurrence is head and tail. There are two methods. If a coin is tossed, first coin, there is a second coin. First coin, a coin is tossed. On first coin, when two coins are tossed, first coin will have a head, or on first coin we may have tail. On first coin, then there is on second coin we may get in the head or tail. On first coin, if you get in the tail, there is chance of getting head, there is chance of getting tail. When two coins are tossed, when a coin is tossed, only the chances are head and tail. When a coin is tossed, only head and tail exists. When two coins are tossed, the output is 4. So there is a tree method. Tree, just like in a tree. Or else it can be denoted in set form as a head, 1 event, head tail, second event, and then tail head, tail. These are the 4 events. Number of outcomes is 4: head, tail head, tail. There is one way. There is also a grid method. When a coin is tossed, there is first coin, second coin, there is one head, there is tail. On second coin, there is second coin, head and tail. So this lines, grids, second grid. So this is a head tail, tail head, tail. This is first coin. This is first coin. This is second coin. So we can write it as a head tail, tail head, tail. These are the 4 events. How many number of possible outcomes are there? 1, 2, 3, 4. The point of interaction of the lines is this. There are 4 events. This is denoted by event E. The possible outcomes are this. Right? There is a case of a coin. If 3 coins are tossed, so what are the outcomes? First head, second one is head, third one is head. Look here, head, tail, next head, tail, next head, tail. If you fix a head here, then the remaining 2 things will have 4 arrangements, as we observed in the last case. If you take tail, tail, head, tail, tail, tail head, tail. If 3 coins are tossed, if the first one fixed as head, remaining chances of or on the 2 coins will be as seen earlier: head, tail head, tail. There's 4 events. If first coin is tossed within the tail, then the possible events becomes 4. So totally 4 plus 4, 8 possibilities are there. This can be shown as in an event head head head, and then head head tail, head tail head, tail head tail tail. Next tail head head, tail head tail, tail tail head, and then tail tail tail. So there are two chances in each coin. On coin, first coin, there are two opportunities. On second coin, two opportunities. On third coin, two opportunities. So total work will be done in 8 ways. So 8 opportunities are there for when 3 coins are tossed. Right. This is the way of writing the events, outputs. When a coin is tossed, when 2 coins are tossed, and when 3 coins are tossed. Let us move on to playing cards. Playing cards I usually would play at home. It's different. Here, it's a pack of cards. It's a pack of cards. In old method, we have only 52 cards. Don't consider jokers and all. We have 52 cards. In these cards, there will be often the shapes like this. 4 shapes. We call this shape, this as a heart card. Heart, and a card is observed with it. There is a heart card. This is in the shape of like this. This is called a club card, club or clover card, and this is a spade or leaf card, and then this is diamond. So these are the things that we observe. Look here, the packs, it contains 52 cards. How we distinguish those 52 cards? How we observe those 52 cards? Those doesn't have an idea, pause this video and look into these things carefully and make a note clearly. This is said to be a card. A set of cards will be of the form A will be there on the card. 2, 3, 4, 5, 6, 7, 8, 9, 10, and the J, Q, K. We call it as Jock, Queen, King. On each shape, there is club cards. Club A's. A will be the symbol here. It will be like this. A. Club A. Club 1. 1 will be there here. And this is a 2. And this is 3, 4, 5, 6, 7. This is a, this sorry 2. This is 3. And this is 4, 5, 6, 7, 8, 9, 10. Jock, Queen, King. So in club cards there are 13 cards. A is 1, this is 2, 3 to 10, and then plus 3, 13 cards. Here 13 cards are there. Those are club cards. Club card means symbol will be like this, just like a tree. Right, next one, diamond card. Diamond A, diamond 2, diamond 3, diamond 4, diamond 5, diamond 6, diamond 7, diamond 8, diamond 9, diamond 10, and then diamond, Jock, Queen, King. In diamond symbol we'll have Ace, 2, 3, 4, 5, 6 numbers, and Jock, Queen, King. So these are 13 cards in diamond. Similarly, with the heart symbol, there will be 13 cards, and with the leaf type, there is spade cards are 13. Each one is called as a shoot. How many shoots are there? 4 shoots are there. In each shoot, there are 13 cards. In each shoot, there are 13 cards. There are totally 52 cards. These cards are called as cards are called as pictured cards. Pictured symbols will be there. Jock, Queen, Kings are there. So we call it as pictured cards. How many pictured cards are there? In club there are 3. In diamond there are 3. In heart there are 3. And in spade there are 3. Therefore 4 into 3. Therefore 12 pictured cards are there. How many A's are there? There are 4 A's, 4 2's, 4 3's, 4 4's, 4 5's, 4 6, 4 7's, 4 8, 4 9, 4 10. This 40 plus 12, 52, total 52 cards. In this diamond card and heart cards are red in color. So these two, how many of these two, when you add these two cards, we'll get these two as 26 red cards will be there. In case of club and spade, club and spade are black in color. The shapes, the club and spade, leaf color and tree color will be in black. Therefore, there are 13 plus 13. 13 club cards, 13 spades cards. Therefore, 26 black cards will be there. 26 black, 26 red cards, 12 in which 12 are pictured cards, in which there are the 4 ace cards, so 4 twos, 4 threes, and then 4 tens respectively. Therefore, there are 52 cards are there in a pack that are given for us in the questions. Don't consider the remaining things that we will play nowadays. Okay, right. These are the things that we have to know in concepts. Right. Next, we go for dice. Die. We know we used to play dice. With the dice, we used to play many games. There is a dot in the die, two dots in the die. So a single dot in the die, two dots are there in the die, three dots are there in the die, four dots are there in the die, 5, 6. When a die is rolled, what is the chance of getting 1? Yes, there is a chance of getting 1, chance of getting 2. So there is a possibility of getting 1, 2, 3, 4, 5, 6. What are the outcomes that we expect from a die? That is taken as an event. So when a die is rolled, we may get 1 or 2, 3, 4, 5, 6. These are the outputs when a die is rolled. When two dice are rolled, two dice are rolled. So what are the possible events? We may get 1, 1. When I die, first die, I write this as first die and this as second die. When I get into 1 on the first die, what are the opportunities that we get on the second die? It may be 1, 2, 3, 4, 5, 6. So 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Right, 6 opportunities when we observe 1 on the first die. If we get into 2 on the first die, it may be 1, 2, 3, 4, 5, 6. So similarly, when we observe 6 on the first die, we observe 1, 2, 3, 4, 5, 6 on the second die. So on first die, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 6. There is 6 events, next 6 events. So that in on 6, when we get into 6 on the first die, we'll get 6 events. Totally, how many events will be there? 6 into 6, that is 36 events. So we'll write those events like this. 1, 1. First on first die, second die, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Okay, right. 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. Next 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6. So like this we can write up to 6, 6. Up to 6, 6. We can write in this events up to 6, 6. So this continues up to 6, 6. There are many questions on this. What is the possibility of getting 2 on the dice? That is only 1. What is the probability of getting 3 on the dice? 2, 1, 1, 2. What is the probability of getting 5, 4 on the dice? 1, 3, 2, 2, 3, 1. 3. What is the probability of getting 5? 1, 4, 2, 3, 3, 2, 4, 1. These are the 4 events. Like this, we will distinguish. Let us look into this thing. Die, sum on the die, sum on die, number of chances. Okay, so what is the sum on the die? If we won't get 1 on the sum as 1, since if we get into 1 plus 1, there is the minimum is 2. So there is 1 comma 1, only 1 chance is there. What is the probability of getting 3? 2 chances, 1, 2, 2, 1. 4, 3 chances. 5, 4 chances. 6, 5 chances. 7, 6 chances will be there. What is the probability? 8. For 8 we will have 5 chances. 8 for 8. Sum as 8. Let us take 1, 7. It's not possible. 2, 6, 6, 2. And then 3, 5, 5, 3. And then 4, 4. There are only 5 chances. So for sum 6 and sum 8 will have only 5. For sum 9 and sum 5 will have only 4. Sum 10 only 3. Sum 11, 5, 6, 6, 5 only 2. And sum 12 only 1. So for 2 and sum 12 and 2 we have, let us see important terms or definitions the probability. First one is a random experiment. Random experiment. An experiment can be conducted any number of times under identical conditions in which each outcome is well known in advance, but the actual outcome cannot be predicted well in advance, is called random experiment. So can you understand? So an experiment, so in chemistry we will do experiment, physics will do experiment. Those experiments doesn't won't consider here. Here random experiment means an experiment can be conducted any number of times under identical conditions in which each outcome is well known. If an experiment is conducted, its outcome is well known, but the actual outcome which is going to appear cannot be predicted. We can't guess well in advance. It's called random experiment. Look here, tossing a coin. When a coin is tossed, either it may turn up, head or tail. We know the outcomes. Outcomes are well known, since if a coin is tossed, head or tail are the outcomes. But which outcome turn up cannot be predicted. So this experiment, tossing a coin, tossing two coins, tossing three coins, tossing a coin is an random experiment. Rolling a die, when a die is rolled, either we'll get 1, 2, 3, 4, 5, 6 dots on the die. We know the outcomes are 6 ways, but the actual outcome which turns up cannot be predicted well in advance. So there is a random experiment. Similarly, picking a cord from the pack of cards, drawing a ball from the bag containing different colored balls. Different colored balls. What is the chance of getting a red ball? No. So I know that I can get a ball from the bag when I draw it without saying it. Then the ball actually that I get into my hand cannot be predicted well in advance. So this experiment is a random experiment. These are the examples for random experiment. Next one, we'll go for another definition. Elementary event and sample space. What is meant by elementary event? Elementary event means each outcome in a random experiment is called elementary event. So when a coin is tossed, what is the elementary event? Elementary events. Elementary events are head, tail. These are called elementary events. The set of elementary events is called, in the random experiment is called a sample space. Sample space, elementary event H, elementary event tail. Only two possibilities when a coin is tossed, so we call this as a sample space. The set of all elementary events in the random experiment is called a sample space. Each outcome in the random experiment is called elementary event. So head is an elementary event, tail is an elementary event. Similarly, when a die is rolled, what is sample space? So 1, 2, 3, 4, 5, 6. This is the sample space. 1 is elementary event, 2 is elementary event, 3 is elementary event. Simply we call it a simple event. Simply we call it as an event or simple event or elementary events. So the set of all elementary events, possible elementary events in a random experiment is called a sample space. Is it clear? Right? What is the number of elements in the sample space? Number of elements in the sample space according to set theory. N of S is equal to order of the set is 2 here when a coin is tossed. Here the order of the set S is 6. N of S is equal to 6. Right? That is the sample space or simple event. When a card is drawn, what is the sample space? Drawing a card from the pack of cards. Since there are 52 cards, what is N of S? N of S is 52C1 according to combinations. Drawing a card from the pack of cards, N of S is 52C1, or 52 opportunities are there in drawing a card. So there is the drawing. There is when a coin is tossed. There is when a die is rolled. There is when a card is picked from the pack of cards. Right. Events, which are said to be events in a random experiment. The subset of the sample space. Sample space we already explained. This any subset of the sample space is called an event. Let us consider a sample space. Let us throw a die. S is equal to 1, 2, 3, 4, 5, 6. Isn't it? This is the sample space when a die is rolled. I create a subset of getting 1, 3, 5 odd number on the die. This is one event. Getting odd number 1, 3, 5. This is one set. This is called this is subset of sample spaces. So we call it as event. E1. What is another E1? Can we guess? Right, two a single element. E1 3 is getting E1 numbers 2, 4, 6. You can create the 2 power 6 subsets. All the subsets are called as events. If you get in the subset as pi, empty set is subset of the given set. This is called impossible event. It's called impossible event. The total subset S is the subset of the given. Total set is the subset of the given set. Therefore, S is equal to 1, 2, 3, 4, 5, 6 is said to be certain event. Total, if you can create 2 power 6 subsets. You can go for sets and you can learn the sets. We are discussing subset of the sample space. Subset of the sample space is called event. So E1 is a event, E2 is a event, E3 is a event. We know that the empty set is the subset of every set, and the given set is becomes the subset. So here null set is called impossible event, and the total set is called certain event. Okay, all right. Equally likely events. Go for equally likely events. In a random experiment, if the events are having equal chances of occurrence, then the events are called equally likely events. Throwing a die. In throwing a die, in throwing a die, sample space is S is equal to 1, 2, 3, 4, 5, 6. E1 is 1. E2 is 2. E3 is 3. E1, E2, E3 are equally likely. 1 out of 6, getting 2 out of 6, getting 3 out of 6 are equally likely events. They have equal chances of appearance. There is 1 by 6, there is 1 by 6, there is 1 by 6. Again, we can create another type of events. E4. E4 is equal to 1, 3, 5. Getting odd number or getting A1 number will have equal chances. Equal chances of appearance. So these are E4 and E5 are equally likely events. Equally likely. Equally likely means they will have equal chances of occurrence. So easy example is when a coin is tossed, getting head and getting tail. Getting head is event 1. Getting head and getting tail are equally likely. What is the possibility of getting head? 1 by 2. What is the possibility of getting tail? 50% chances. They are equally likely events. So if an experiment is conducted, if the events are having equal chances of occurrence, then the events are called equally likely events. Next one, mutually exclusive events. If they're in the random experiment, if the happening of one event prevents the happening of the other events, then the events are called mutually exclusive events. Suppose head and tail. I consider an example here. My event E1 is getting head. My event E2 is getting tail. In tossing a coin, up, if head appears, then certainly it prevents the appearance of tail. If we toss a coin, if tail appears, on the coin, certainly it prevented head. So E1 and E2 in tossing a coin are mutually exclusive, or mathematically we can say that if E1 intersection E2 is equal to pi, there is no element in the set. If it is an empty set, then we say that E1 and E2 are mutually exclusive. Okay. Next example, in rolling a die, what is sample space? S is equal to 1, 2, 3, 4, 5, 6. So let us consider an event E1 as getting odd numbers on the die, and E2 is the event of getting even number on the die. Possibility of getting even number, possibility of getting a odd number. E1 and E2. Even number, if you 135 appears on the die, certainly we can say that 246 doesn't appear. So if E1 is appeared on the die, the elements in E1 is appeared on the die, it prevents E2 elements. Therefore, E1 and E2 are mutually exclusive. Clearly, mathematically, I can say that E1 intersection E2 is equal to pi. Therefore, E1 and E2 are called mutually exclusive events. Mutually exclusive events. 1, 2, 3, 4, 5, 6. Each and every element, if you take as an event, elementary events in the sample space are mutually exclusive. They are equally likely, they are mutually exclusive. 1, 2, 3, 4, 5, 6. Individually, they are equally likely. If one appears, it prevents all the elements, all the events. So, 1 is mutually exclusive with the remaining. 1 mutually exclusive, 2 is mutually exclusive, 3 is mutually exclusive. So, they are mutually exclusive events. Okay. Right, next we'll go for another example, another definition. Exhaustive events. Exhaustive events. In a trial, the set of all possible elementary events is called exhaustive event. So if a coin is tossed, sample space is nothing but exhaustive event H T. In some cases, sample space becomes the exhaustive event. The set of all possible elementary events is called sample space here also. If a random experiment is conducted, if it trial means a single experiment. A single experiment is called a trial. In a trial, the elementary events, the set of all elementary events is called exhaustive event. Clearly, we go for mathematical definition. I consider the sample space of rolling a die. So let us consider E1. E1 is 1, 3, 5, getting odd numbers. E2 is getting even numbers. What is the E1 union E2? If you add these two sets, union of these two sets is sample space, then E1 and E2 are called exhaustive events. So remember the mathematical definition. If E1, E2 are any two events in the sample space, then E1 union E2 is equal to S, that is called exhaustive event. If E1 intersection E2 is equal to pi, then E1 and E2 are called mutually exclusive events. Mutually exclusive. If the chance of occurrence of E1 and E2 are having same, then they are called equally likely events. If they have same chances of appearance, then they are called equally likely. If one event prevents the other event, then they are mutually exclusive, or even intersection E2 is equal to pi. If the union of events is sample space, then the events given are called exhaustive events. Suppose A is an event in the sample space, I consider 1, 2, and B is the event in the sample space as 2, 3, 4, and C is the event in the sample space as 3, 4, 5, 6. A union B union C is equal to S. Therefore, A, B, C are called exhaustive events. Union becomes sample space. Then A, B, C are called exhaustive events. For giving examples, it's very useful. These examples are useful in giving examples for mutual exclusive, not equally likely, mutual exclusive, equally likely, mutually exclusive, equally likely events. These are different types of conditions can be proved using examples, right? favorable and unfavorable events. In a random experiment, the events that are favorable are called favorable events, and the events that are not favorable are called unfavorable events. So let us take an example here. Uh, S is the sample space of a random experiment 1, 2, 3, 4, 5. My event is my event is 2, 3, 4. We all know how to play in the game. When a die is rolled, I ask, then it appears 2. If 2 appears, I win the game. If 2 appears, I will say that I win the game. So here my opportunity is if 2, 3, 4 appears, I win the game. So what I guess, what I choose to win is said to be favorable. So E is equal to 2, 3, 4. This is favorable. What are unfavorable events? The remaining events which are not favorable, are denoted as 1, 5, 6. These are unfavorable events. If I choose the favorable events, certainly, indirectly, unfavorable events will be separated in the random experiment. Okay, when a coin is tossed twice, when a coin is tossed twice, the sample space is head, 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 tail, tail, head, and then tail, tail. This is the sample space. My favorable event is getting heads. Then what are unfavorable events? The unfavorable events are denoted by E bar. If E is a HH, E bar becomes the unfavorable events are in the HT, TH, and TT. If I consider this as favorable, this becomes unfavorable. So events that are favorable are called favorable events, and the events which are not favorable are called unfavorable events. Next, complementary events. In a random experiment, E within the event that is favorable. The complementary event of E is E bar, nothing but E dash, E power C, E complement. This is also the notation for the complementary event. Nothing but total sample space minus favorable events is the unfavorable event. So if E and E are said to be complementary events, if and only if E intersection E bar is 5 and E union E bar is equal to S. If it satisfies these two conditions, E and E bar, then those two events are said to be complementary events. A intersection B is equal to pi and A union B is equal to S, then A and B are called the complementary events. One is the complementary of the other. Right. Let us take an example. Let S be the sample space. Let S be the sample space of in throwing a die. I consider the event as E1 as 135. E1 as 135. Then this is a favorable event. What is unfavorable event? Sample space minus favorable. So 1, 3, 1, 2, 3, 4, 5, 6 minus 1, 2, 1, 3, 5 is nothing but 2, 4, 6. If you add these two events, E intersection E bar. What is E intersection E bar? Getting odd number on the die is favorable. Getting even number on the die is unfavorable. E intersection E bar is 5. Therefore, first condition satisfied. Next, E union E bar. What is union of these two? 1, 2, 3, 4, 5, 6. Therefore, which is nothing but sample. So, E union E bar is equal to sample space and E intersection E bar is equal to 5. Therefore, E and E bar are called complementary events. So, if E bar is a unfavorable event, then S minus favorable event is nothing but complementary event. Complementary event is also denoted by E cap or E bar or E dash. So, there is the notation for complementary event. Right, next we go for another definition here, important definition. Certain event or impossible event. Certain event or impossible event. If the event in the random experiment is certain, then the event is called a certain event. Already I discussed about this. And the event which is impossible in the experiment is called impossible event. Null set is the impossible event in the sample space, and certain sample space is the certain event. So S is a certain event, and the subset and the null set of the sample space is called a impossible event. The event that is not possible in this random experiment. If a random experiment is conducted, I don't know, if you choose an impossible event that is not possible, and that in that particular in the random experiment, then that event is said to be impossible event. Impossible event. The possibility of occurrence of impossible event is 0. The possibility of occurrence of certain event is 1. Okay. All right. Next. Go for the next definition. Classical definition of probability. In a random experiment, there are n mutually exclusive, n equally likely, and n exhaustive events. N mutually exclusive, equally likely, exhaustive events in which there are m favorable events are there. That is the event E contains m favorable events. Then the probability of that event E is defined as P of E is the notation for the probability of the event E, denoted by P of E is equal to m by n. Favorable events by total number of events. Number of favorable events by total number of events is the probability of the event E. So usually we used to write the probability of the event. Suppose what is the probability of getting head when a coin is tossed? It is 1 by 2. We all know about this. What is the probability of getting tail? 1 by 2. 50% chances of getting head and tail. What is the classical definition says? Favorable event. Head is the favorable event. Total number of events is head and tail. So 1 by 2 is the probability of getting head. What is the probability of getting tail? 1 by 2. When a die is rolled, what is the probability of getting 1 on the die? 1 is favorable. Total number of events is 1 by 6. What is the probability of getting 2? 1 by 6. What is the probability of getting 3? 1 by 6. So probability of getting 6, 1 by 6. So 1 by 6, 1 by 6, they are equally likely. Getting head and tail are mutually exclusive. Head intersection tail becomes a pi. Head union tail becomes sample space, exhaustive event. So if there are n mutual exclusive, equally likely and exhaustive events in which m are favorable events and the event is denoted by E, then the probability of the event E, that is P of E, is defined as P of E is equal to number of favorable events by total number of events. Okay. So what is the probability of getting a 1 or 2 or 3 or 4 or 5, 6? This becomes P of 1 plus P of 2 plus P of 3 plus P of 6. P of 6, that is 1 by 6 plus 1 by 6 plus 6 times. So 6 times of 1 by 6 becomes 1. So probability of certain event is 1. What is the probability of getting impossible event? What is the probability of 5? Probability of null set is 0. So probability of impossible event is 0. Probability of certain event is 1. Right. Next here. E bar. If E is the favorable event, E bar becomes the unfavorable event. So what is the probability of unfavorable event means? Favorable events are M. If you subtract M from total events, that is S minus E. So what is the complementary event? S minus E. That is N minus M is the unfavorable events. Total minus favorable becomes unfavorable. Unfavorable by total number of events. So unfavorable events, number of unfavorable events by total number of events is the probability of unfavorable events. So n minus n by n. N by n minus m by n. N by n becomes 1 minus m by n becomes P of E. So P of E bar is nothing but 1 minus P of E. P of E bar plus P of E is equal to 1. In general, the probability of a favorable event, the probability of success, favorable means that is required. So that is said to be the success, the probability of winning. So probability of success is denoted by P and the probability of failure is denoted by Q. So P is P of E and Q is P of E bar. The sum is 1. P of E plus P of E bar is equal to 1. Make a note that P is the favorable event, Q is unfavorable event. Therefore, favorable event plus unfavorable event in a random experiment is 1. So, what is the probability of how P is defined means? Come here, if in a trail, Let S be in the sample space of a random experiment. Then the function P, S mapping to P mapping from S to R is said to be a probability function if it satisfies the following three axioms. Properties or axioms, principles. The first one is, if you take any probability of the event, it must be greater than or equal to 0. Probability always lies between, the probability of success always lies between 0 and 1. 0 is impossible event probability, 1 is certain event probability. So probability always lies between 0 to 1. What is the probability of getting head? 1 by 2. Probability of getting 3 on the die? 1 by 6. Probability of getting 1, 3, 5 on the die? 3 by 6. So 3 favorable. So 1, 3, 5. Odd number on the die means there are three odd numbers. So favorable events are 3. By total number of events is 6. So this is 3 by 6. So here if you take the chance of appearance, it will be less than or equal to 1 and greater than 0. Probability is always positive, or chance of occurrence is always positive. So where E is the event in the sample space, P of E is greater than or equal to 0. So this is called a non-negative axiom, positive axiom, positive axiom of the probability function. Next, if S is the sample space, then the probability of sample space is 1. So if head and tail are in the events in the sample space in throwing a die, in tossing a coin, what is the probability of S? Probability of nothing but probability of head plus probability of tail. Probability of head is 1 by 2, probability of tail is 1 by 2, sum is 1. So this is called a certain event. Since the probability is equal to 1, we call it a certain event. So this axiom is called a certain axiom. Certainty, axiom of certainty, axiom of non-negativity or positivity. And then even E2 belongs to S, and even intersection E2 is equal to pi. Even in the E2 are mutual exclusive, and even E2 are in the events in the sample space. Then P of E1 union E2 is equal to P of E1 plus P of E2. This is called additive axiom or axiom of additivity. So if P, if the function mapping from S to R satisfies these three axioms, follows these three properties. If three axioms are followed by P, then P is called probability function. Everyone must learn this so that only you can understand many of the problems. A P of E must be greater than or equal to 0, or a P lies between 0 and 1. So probability is always positive. So axiom of non-negativity. P of S is equal to 1, axiom of certainty. And even in the E2 or in the mutual exclusive events, P of E1 union E2 is equal to P of E1 plus P of E2. Union becomes summation. Union becomes summation, that is additive. Adding P of A union B union C becomes P of A plus P of B plus P of C, where A, B, C are mutual exclusive. This is called additivity. Union. The probability of union of three events becomes the sum of the probabilities of the events. Therefore, this is called additive axiom. Additive axiom of probability function. There is certain axiom of probability function. There is the positive axiom of probability function. So probability function satisfies three conditions: P of E greater than or equal to 0, P of S is equal to 1, P of E1 union E2 is equal to P of E1 plus P of E2, where E1 and E2 are mutual exclusive. Given question is exercise 9a problems. We'll discuss problem now. In the experiment of throwing a die, consider the following events. A is equal to 135, and then B is equal to 246, C is equal to 123. Are they equally likely? That is the question given. In throwing a die, what is the sample space? Sample space S is equal to 1, 2, 3, 4, 5, 6. There is sample space. Given A is equal to 1 to 3. So number of elements present in S is total number of events is 6. What is A? A is equal to 135. So number of elements present in A is 3. What is B? 246. Number of elements present in B is 3. What is the number of elements present in C? C given it is 1 2 3 itself. 1 2 3. Therefore, number of elements present in C is 3. What is the probability of A? What is chances of A occurrence? Favorable events. A, number of events, favorable events by total number of events. So, which is nothing but P of B, 3 by 6, and which is nothing but P of C. They have equal chances of occurrence. Number of elements in A, number of elements in B, number of elements in C are equal. Therefore, they will have equal chances of occurrence. Therefore, A, B, C are equally likely events. Probability of A is 1 by 2. Probability of B is 1 by 2. Probability of C is 1 by 2. Favorable events by total number of events. Favorable events by total number of events. Favorable events by total. So P of A, P of B, P of C has same probability. Probability means chances of occurrence. Right? So first one, they are equally likely events. We go for the next one. If the experiment of throwing a in the experiment of throwing a die, consider the following events. When a die is thrown, only a single die is thrown. Therefore, sample space S is equal to 1, 2, 3, 4, 5, 6. Right. So what is A? A is equal to 135. B is equal to 4. C is equal to 6. Are they mutual exclusive? Yes. Consider A intersection B. A intersection B is equal to null set. What is B intersection C? It's a null set. What is C intersection A? C intersection is also null set. So intersection between any two events is pi. Therefore, ABC are mutually exclusive. Mutually exclusive. Very easy question. Next one. In the experiment of throwing a die, consider the following events. Are they exhaustive events? We know that sample space in the random experiment. In this random experiment, sample space S is equal to 1, 2, 3, 4, 5, 6. Right. What is A? 2, 4, 6. What is B? 3, 6. What is C? 1, 5, 6. Are they equally likely? This contains 3, this contains 2. No, they are not equally likely. Are they mutually exclusive? Here the intersection point is 6. Here the intersection is 6. Therefore, it's not equal to pi. Therefore, they are not mutually exclusive. Are they exhaustive? Our question is, are they exhaustive? So, let us consider the union of the sets. If the union of the sets is equal to sample space, then we say that they are exhaustive. If it is not equal to S, they are not exhaustive ones. So union of these three sets, one is there in C and 2 in A, 3 in B, 4 in A, 5 in C, 6 in all. Therefore, there is nothing but sample space S. A union B is union C is equal to S. Therefore, given events A, B, C are exhaustive events. Given events are exhaustive events. Next one. Second Roman, give two examples of mutually exclusive and exhaustive. They must be mutually exclusive and also exhaustive. Let us give an example. First example. Example 1, I taking example 1. Rolling, tossing two coins. Tossing two coins, sample space S is equal to. What is sample space? Head, 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 tail, tail, head, and tail, tail. There is sample space. Let us consider event E1. E1 is the event that is a head, head, tail, tail. Both heads or both tails is my favorable event. And then I consider E2. E2 has a head, tail, tail, head. This is it. So what is E1 union E2? E1 union E2. If you add these two things, it becomes sample space. What is E1 intersection E2? This becomes pi, null set. So what you can conclude? They are complementary events, mutual exclusive and exhaustive. Therefore, E1 and E2 are both mutual exclusive and exhaustive event. That is the first example. We go for the next example, rolling a die. Rolling a die, my sample space is 1, 2, 3, 4, 5, 6. This sample space. Let us consider an event A as 1, 3, 5 and event B as 2, 4, 6. Here E1 and E2 are equally likely. Here also equally likely. Mutual exclusive, I consider A intersection B. These odd numbers, these even numbers, there are no point of intersection, null set. A union B, all even, all are there, all even are there. There is nothing but 1, 2, 3, 4, 5, 6. Therefore, it is nothing but sample space. Therefore, A and B are mutually exclusive, mutually exclusive, and also mutual exclusive and exhaustive events. So, this is the easy and simple examples to make the events to be mutually exclusive and exhaustive events. Right, next we go for the next problem. Give two examples of the events that are neither mutually exclusive nor exhaustive. They must not be mutually exclusive nor exhaustive. I consider the same example. I consider an example here. Example 1. Tossing two coins. Tossing two coins is my experiment. Tossing two coins is my experiment, in which the sample space S is nothing but sample space. Sample space is nothing but head head, head tail, tail head, and then a tail tail. This is my sample space. I consider an event E1 as like this. Event E1 is head head. Event 2 is mutual exclusive or not exhaustive. My event is this head tail. Tail head is my second experiment. What is E1 intersection E2? This head tail, tail head. Okay. So what is E1 intersection E2? E1 intersection E2 is head head. So not equal to pi. And then what is E1 union E2? E1 union E2 is union of these two sets is head head and tail head, which is not equal to sample space. So these two events are neither mutual exclusive nor exhaustive. So if E1 intersection E2 is equal to pi and E1 union E2 is equal to S according to definition, then only they are said to be mutual exclusive and exhaustive events. Here it is not equal to pi and not equal to S. Therefore, they are neither mutual exclusive nor exhaustive. Therefore, go for second example, rolling a die. Rolling a die is my experiment. My experiment is rolling a die. The sample space S is equal to 1, 2, 3, 4, 5, 6. So I consider event A as 1, 2, 3 and B as 3, 4, 5. So what is A intersection B? A intersection B is 3, which is not equal to pi. Therefore, it's not a mutually exclusive one. What is A union B? A union B is nothing but 1, 2, 3, 4, 5. 6 is not, this is not equal to S. Therefore, A and B are neither mutually exclusive nor exhaustive one. These are the two simple examples to say that they are neither mutually exclusive nor exhaustive. Last problem in this exercise. Give two examples of the events that are neither equally likely nor exhaustive. Equally likely nor exhaustive. Let us consider the same example here. Two coins. They are not equally likely. They are exhaustive. Equal chances of occurrence is not there. So they are not equally likely and not exhaustive. This is the best example. I'll write here. Example 1. Tossing two coins is my experiment, and then sample space is H H, head tail, tail head, tail tail. This is sample space. I consider an event E1 as head head and E2 as tail tail head, 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 tail. So what is the E1 intersection? What is the probability of E1? Is the probability of E1 is favorable event by total number of events. What is the probability of E2? Chance of E2 is 3 by 4. This will have 1 by 4 chance, this will have 3 by 4 chance. Therefore, they are not equally likely. They are not equally likely. Therefore, E1 union E2 is head, head, tail, tail, head, tail, which is not equal to sample space. Therefore, E1 and E2 are both are not equally likely and exhaust to events. Let us consider another example here. Rolling a die. Rolling a die. Sample spaces is equal to 1, 2, 3, 4, 5, 6. I consider the event A as 1, 2 and B as 2, 3, 4, 5. So what is the probability of A? Number of elements in A, n of A by total number of elements means sample space. Number of elements in sample space, that is 2 by 6, which is 1 by 3. What is the probability of B? Number of elements in B by number of elements in S. My favorable events in B are 4 by total number of elements is 6. There is 2 by 3. These two are not equal. So chances of A and chances of B are in the 1 by 3 and 2 by 3. They are not equally likely events. So and also what is A union B? A union B is nothing but 1, 2, 3, 4, 5. 6 is missing here, not equal to sample space. Therefore, they are not exhaustive. These are the examples from the two examples which says that they are neither equally likely nor exhaustive.